So here goes. So we've got 2 sections to do today. We'll definitely get through the first one. I don't know how much of the second one we will get through, but the first one, section 11.5, you got the sheet in front of you. It's talking about problems called and or problems. So if you, I know it's been a long time. When we talked about tree diagrams, I prefaced our whole discussion by saying, okay, up to that point, we've been talking about the probability of what's called a simple event, meaning the event of what is one thing happening. So when I roll a die, what's the probability I roll a 4? When I draw a card, what's the probability it's red? So just the probability of one thing. Now we are going to deal with probabilities when I am combining things. So this is called our compound probability. So the first type of compound event is the probability of an or. Okay, so a first thing or a second thing happening. So I've just got right there for you the formula so that you can know. The probability of event A happening or event B happening is given by this. So here's my probability. A or B is in parentheses. And then I get that's equal to the probability of A plus the probability of B minus the probability of A or B. So you might just be wondering, hey, why do I have to do that subtraction? Which is a really great question. And so I just real quick want to remind you, this is thinking way, way back in the past to our first unit when we were dealing with sets. And we were talking about the union. And we had a formula that was very similar to this for the number of elements that are in A union B. Okay, so this is good review for the final exam that we got coming up in a few weeks. So the number of elements that are in A union B. And when we did this, we counted all the elements in A, right? So I'm just going to shade to the down and left for A. Then we added all the elements in B, so I'm going to shade down and to the right for B. But then way back when, I drew this on the board, or I drew this somewhere. What do we notice happen? What elements did I count twice? Yeah, the ones in the middle, which is where the intersection is. So what we did back then is we had to subtract the number of elements in the intersection, A intersect B. Well, the only reason I mentioned that, in all honesty, the only reason I mentioned that back when we talked about sets was to get ready for this. Okay, so if we investigated it further, there is a relationship between sets and probability, but we're not going to go that deep. But here's what I need you to realize is this probability formula for an or event, one thing happening or another thing happening, that is based on this number of elements in the union that we talked about way back when. So when you do this, you find the probability of event A happening plus the probability of event B happening, then you subtract the probability that they happen at the same time. All right, so let's go ahead and do a bunch of problems so we can get used to that. So my example right there says one card is selected from a standard deck of playing cards. Okay, so if in your notes, if you have that picture, if you need it, I didn't reprint it. Determine the probability of the following, the probability of an ace or a 9. Okay, well, here goes. To find this, we're going to find the probability of an ace. Then we're going to add to that the probability of a 9. Then we are going to subtract the probability that those two things happen together, the ace and the 9 happen at the same time. All right, so thinking about this, the probability of an ace. We did a real quick rundown of what probability was just a moment ago, but remind me, how many aces are there in the deck of cards? There are 4. Does anyone remember how many cards are in the deck of cards? 52, okay, great. Plus 9s. How many 9s are there in the deck of cards? Okay, there are 4. And then divided by, again, 52. Now minus, can you get, if you draw one card, okay, we're just drawing one card, can you get an ace and a 9 at the same time? No, those two things don't happen at the same time. So there are 0 cards that have an ace and a 9 at the same time out of 52. And so that is, if you remember, you're adding of fractions, 4 over 52 plus 4 over 52 becomes 8 over 52. And remember, I know it's been a while, you can either reduce your fraction or you can make a decimal out of it. I'm going to make a decimal. I'm going to just divide these and go to 4 decimal places. And so that's going to be 0.1538. The reason I picked that as my first example is when you have a situation like this where it is impossible for two things to happen at the same time, that is called a mutually exclusive event. So if you've ever heard those words used, or if you've ever used those words, when you say two things are mutually exclusive, you're saying that they cannot happen at the same time. So mutually exclusive, they are events that cannot occur simultaneously. All right, so we're just going to do this a bunch of times so that you can get used to doing the probability of OR events. So once you have written down what mutually exclusive is, go ahead and do the B problem, the probability of an ace or a heart. I'll give you a hint. Those are not mutually exclusive. Okay, there is going to be a probability of those happening at the same time. See if you can figure that one out. I'm sorry, what'd you say? Yes. Good recollection. All right, for the first couple, I'm going to write the whole thing out just so you can see how the formula is working. When we get down to the problems where there's a little less room, I'm not going to write the whole thing. So to find the probability of an ace or a heart, you've got to find first the probability of an ace, add to that the probability of a heart, and then subtract the probability that those things happen at the same time. So we already saw the probability of an ace is 4 out of 52. I'm going to rewrite that. What's the probability of a heart? 13, yes, there's 13 of them out of 52. And now subtract, can an ace and a heart happen at the same time? Yes, how many aces are with hearts on them are there? There's just one. So I'm going to subtract that 1 out of 52. Okay. All those have a common denominator, which makes our job just a little bit easier. So 4 plus 13 is 17, minus 1 is 16 out of 52. Again, you can reduce that fraction. I'm going to divide and give a 4-digit decimal. And if you did the same thing, then you have written down 0.3077. So far, so good? All right, do the C problem, please. All right, so to find the probability of this OR event, I'm going to find the probability of red plus the probability of black minus the probability those two things happen the same time. So here we go. How many red cards are there? 26 out of 52. How many black cards are there? How many cards have both? Yeah, these are mutually exclusive. When you pick a card, it's either red or black, one of those two. But we see that 26 plus 26 is 52 out of 52. So the probability that we pick a red or a black card is 1, which hopefully makes some semblance of sense. All right, one more of these based on the deck of cards. Go ahead and do the D problem, the probability of a picture card or a red card. Remember, picture cards are the jacks, the queens, the kings. There's 3 picture cards of each suit. All right, so to find the probability of a picture card or a red card, I got to first find the probability of a picture card plus the probability of a red card minus the probability that those two things happen at the same time. So picture cards, how many of those do I have? Yep, 12 out of 52 is that probability. Is anyone having a problem calculating these probabilities? We doing okay? Okay, please let me know. Okay, I want you to do amazing on this test. And I know that everybody could use a good test grade, and I want you to get it. Red cards, we already saw. There's 26 out of 52. And then how many cards are there that are both red and a picture card? Yeah, 6 of them. There's going to be half of the cards are going to be, so 6 out of 52. There's the diamonds and the hearts, and then there's a picture card for each, 3 picture cards for each of them. So now they all have common denominator. 12 plus 26 is 38. 38 minus 6 is 32 out of 52. Once again, you can reduce that, or I'm just going to take the calculator way, and I get 0.6154. We're just going to do a few more. Okay, I'm changing the picture just to make sure that you're understanding the process, not just able to do it with a deck of cards. So example 2, I give you a different deck. There's 20 cards to this deck. There's different animals. There's different numbers. So go ahead and do the A problem, please. The probability of a lion or an even number. All right, so I'm not going to write out the whole formula. If that bothers you, please let me know. But to find the probability of a lion or an even number, I'm going to find the probability of a lion plus the probability of an even minus the probability that those two things happen at the same time. All right, what's the probability of a lion? Yep, there are 5 lions out of the 20 cards. Great. What's the probability of an even number? Yep, there's 4 twos, there's 4 fours. So that's 8 out of 20. Great. Minus, are there any lions that are even numbers? Yeah, there's the 2 here and the 4 here. So that is 2 lions. So there's 2 cards that those 2 things happen at the same time. So 5 plus 8 is 13, minus 2 is 11 out of 20. You can leave that answer just like that because it is fully reduced. Or if you feel like doing a little bit extra, that is 0.55. All right, if you feel good about that, do the next one. If you don't feel good about that, I hope you ask me a question because I am here to answer it. Excuse me. All right, so probably the yellow bird or a number less than 3. So what's the probability of a yellow bird? Yep, great job. If you're having trouble finding probabilities, okay, remember I told you section 1 is the whole chapter was summarized in section 1. Let's talk. Okay, again, I don't want you to sit there feeling stupefied when we can fix this. What's the probability of a number less than 3? 8, yes. So it's not less than or equal to, it's less than. And then minus, how many yellow birds and numbers less than 3 happen at the same time? Yep, 1. So that is 2 plus 8 is 10, minus 1, that's 9 out of 20, which you can leave just like that. Or you can say that that's going to be 0.45 if you want to make a decimal. Okay, I'm going to go a little bit quicker in the next few. I feel like we're getting sort of used to it, but if you don't have enough time, let me know. Do the C part. A lion or a 3? All right, probability of a lion. We've already done that. That's 5 out of 20. We saw that in the A problem. Plus, what's the probability that I get a 3? Yep, thank you very much. 4 out of 20. And can those things happen at the same time? Yep, once. So 5 plus 4 is 8, minus 1, or excuse me, 5 plus 4 is 9, actually. Minus 1 is 8 out of 20. And if you reduce that, that's great. Or you made it a decimal, it's 0.40. Okay, just 2 more OR problems. So if you have a question about how to do the OR, you're running out of time to ask it. So red bird or an even number, why don't you do both of them? Let's just knock them both out. And then yellow bird or frog, and then we will take care of both of those. All right, so a red bird. The probability of a red bird is 3 out of 20. Anybody get anything different on that? If you got something different than me, let me know. Let's talk. Okay, the probability of an even number. We've already done that one. That's 8 out of 20. And then minus, can a red bird and an even number happen at the same time? And the answer is yes, that happens once. And so 3 plus 8 is 11, minus 1 is 10 out of 20. So you got a 50-50 shot of picking a red bird or an even number when you draw randomly from this deck. We still okay? The last or problem for us. The probability of a yellow bird or a frog. Okay, well, yellow bird we've already done once. That was 2 out of 20. Frogs are the same as lions. They're going to be 5 out of 20. Minus, can a yellow bird and a frog happen at the same time? So these two events, yellow bird and frog, they are called what? Boom, yes, mutually exclusive. Thank you very much. And so that is 7 out of 20, and 7 out of 20 is 0.35 if you want to make a decimal out of it. Okay, so that is our OR event. Now notice this about the OR event, because we're going to move on to AND event. All of these OR event problems have been one trial. So this particular AND that we talked about up here, this is the probability of two things happening at the same time, simultaneously. Okay, so this is simultaneous. I think I spelled that right. Okay, so A and B happening in this situation, that is, can they happen at the same time? That is a different AND. Okay, I know this is a little bit confusing. The book puts both of these in the same section. That is a different AND than this AND right here. So the next thing we're going to talk about is the probability of A and B happening. This is the situation where you have two or more trials. And this and right here, when we use this and, it has the implication of and then. There's order to it. So I need you to see the difference and make sure that you're kind of tracking. In the first bunch of problems we just did, the word and there meant, can these two things happen at the same time? This new and means, okay, we're going to do two things. Does A happen and then B happen? So it's different. Now, the probability, once you get that distinction, the probability is nice and straightforward. When you go to find the probability of A and then B happening, it's based on the counting principle, which we talked about before we left for spring break. That's the probability of A happening times the probability of B happening, and you're done. Okay, so here we go. Example 3. This is going to be my example. We're going to put two cards. So this is important. I'm going to circle it. Okay, that's what makes this an and problem, is we're doing two or more of something. Two cards are selected with replacement. I know it's been a while. What does with replacement mean? What detail do those words tell us? You're putting the card back. Okay, it's a different problem if we do this without replacement, and we will on the second page. Okay, two cards are selected with replacement from the standard deck. Find the probability of two diamonds. Okay, so the probability of a diamond and a diamond. That's what probability of two diamonds means. I'm finding the probability of a diamond and then a diamond. All right, well, help me out. The first card, what's the probability of the first one when I pick it? Is a diamond. Perfect, thank you very much. 13 out of 52, I love it. Then I replace that card. And now I draw again. What's the probability the second one is a diamond? That is excellent, 13 out of 52. Wonderful. If you're going to make just a little suggestion, if you're going to work with the fractions and reduce them, I would suggest reducing first. Okay, or if you're just going to make decimals, then you're just popping this into your calculator. So I'm going to do it both ways on this one. So first, if you're making it decimals, okay, it's 13 times 13, and then you're going to divide by 52, and then divide by 52, and you get 0.0625. So make sure you're able to use your calculator effectively and get that. Bless you. Oh, no, that makes me sad. All right, so if you're going to reduce these fractions, though, 13 goes into 13 once, 13 goes into 52 four times. That happens both ways. And so then in the top, 1 times 1 is 1, 4 times 4 is 16. There's the reduced fraction if you prefer that. What it is you're allergic to fractions, not my classroom. All right, so we're going to flip the page. I would like you to give this one a try. You're going to do the same thing we just did, the probability of 2 diamonds, but this time you're doing it without replacement. So that's going to change things a little bit. It's going to change the probability of the second one just a wee tiny bit. Okay, so let's give this a try. And if you have a misconception or anything, let me know. So we're going to find the probability of the diamond and then a diamond when I draw twice. So what's the probability the first card's a diamond? Perfect, that doesn't change. 13 out of 52. But this time, we are not replacing that card. Okay, we're playing some Texas Hold'em. Okay, we're holding that diamond to on the ground. Okay, so now what's the probably the next one's a diamond? So here's the question: how many diamonds are left in the deck? Out of how many cards? Oh, beautiful. Well done. 12 out of 51. Okay, we spent a bunch of time before spring break talking. I think all of you were here, so we spent a lot of time talking about the difference between with and without replacement. I'm not going to bother reducing. I'm going to do this. So just make sure you're getting the same decimals as me. So I'm going to take 13 and I'm going to multiply by the 12, and then I'm going to divide by 52, and then I'm going to divide by 51. And so then I get 0.0588. Just as an aside, because it might come up as part of your homework. Let's say we were drawing 3 cards, and I want to know what the probability of getting 3 diamonds. Okay, so and we're doing it without replacement. The first one's 13 out of 52. The next one's 12 out of 51. What would be the probability the next one was a diamond? Oh, you guys got it. Great job. Catching on really lovely. So that is the idea of what's called independent events. 2 events are independent if the first one happening does not change the probability of the second. Okay, so independent events, 2 events are independent if the first one occurring does not affect the probability of the second. What that means is example 3, the one at the bottom of the previous page, example 3 were independent events. Because when I did that with replacement, picking a diamond the first time did not change the probability of getting a diamond the second time. Example 4, when I did it without replacement, getting a diamond the first time changed the probability of getting a diamond the second time, and so these would be called dependent events. Okay, dependent is just the opposite of independent. So example 5 says we're going to use the deck of cards on the previous page that is pictured, so you can flip forward if you need to. And I would like you to do those four problems, A, B, C, and D. Notice you're doing it the first time around with replacement. All right, so I'm going to get started on these. So the first one is the probability of 2 3s. So what's the probability of a 3 and then a 3? Again, we're doing this with replacement. Whatever card we pick, we're putting back and can be chosen again. So when I do that, what's the probability the first one's a 3? Yep, 4 out of 20. Great. And so then when I replace it, the probability the second one is a 3, again, is 4 out of 20. And so that is 4 times 4 is 16, divided by 20 is going to be 0.04. The probability of a lion and then a monkey, okay? Well, what's the probability of a lion? Yep, indeed, 5 out of 20. And then a monkey, I think, is the same thing, 5 out of 20. And so that is 25 divided by 20 divided by 20. And I believe that we are going to get 0.0625. Probably have a frog and a yellow bird. I think there's 5 frogs, so 5 out of 20. But then yellow bird is a little different. Is yellow bird 2 or is it 3? It's 2. It's 2. I'm assuming I heard what you said. Okay, thank you. 2 out of 20, great. And so that is going to be 10 divided by 20 divided by 20, and that turns out to be 0.025. And then the last one, what's the probability? They're both even numbers. And so even numbers, how many evens are there? 8. Okay, so that's going to be 8 out of 20 for both of them. So that is 64 divided by 20 divided by 20, and I get 0.16. Anybody having any issue with any of those? Okay, I'm assuming you tell me the truth. There's not a lot of you in here. We could get all your questions answered, no problem. So example 6 says, okay, do the same problem, but now do it without replacement. So without replacement, I'm just going to draw a little line here. We're going to do the same one on the other side of this line. So go ahead. I'm going to give you a couple minutes to go and make as much progress as you can. You are doing this without replacing the first card. So, for instance, on the A problem, let me talk you through the A problem and see if it answers your question. Okay, so the A problem, we're going to do this now without replacement. So I'm doing these in blue right over here. So the probability of 2 3s. Well, okay, so we go to the picture on the front. What's the probability I pick a 3? Okay, so now here's what I assume. I've got a 3 in my hand. I've picked one. Okay, I'm not putting it back into the deck. So now, for the second one to be a 3, how many 3s are left in the deck? 3. Out of how many cards are left in the deck? 19. Does that make it a little better? Great. I'm just going to do some division while you guys are working the problem. 12 divided by 20 divided by 19. And that's 0.0026. All right, the next one's lion and monkey. So what's the probability of a lion? We already saw that. I'm going to give that one to you. That's 5 out of 20. Now, here's the thing. I am now holding a lion in my hand. And now I want to know what's the probability now that the next card's a monkey. Well, how many monkeys are left in the deck? There's still 5. Exactly. I haven't touched the monkeys. And now how many cards are left in the deck? Ah, yes, but the number of cards have changed. Is everyone tracking with me on that? Okay, because I know it's not necessarily super obvious. So I got 25 divided by 20 divided by 19. It turns out to be 0.0658. Okay, fantastic. The next one, the probability of a frog and a yellow bird. Well, the probability of a frog is going to stay 5 out of 20. So now again, I've got a frog in my hand. What's the probability that the next card's a yellow bird? How many yellow birds are in the deck? Still 2 out of how many cards? 19, because I have the frog in my hand. Great. So that's 10 divided by 20 divided by 19, and that turns out to be 0.0263. And last but not least, both even numbers. Again, the first one being an even number is 8 out of 20. So now I have some even numbered card in my hand. So for the second one, how many even numbered cards are left in the deck? Out of how many cards? Beautiful. Well done. Excellent by all of you. 8 times 7 is 56 divided by 20 divided by 19. And I get 0.1474. If you're feeling okay about that, yes. You got, for this one right here that I'm pointing to, you got a different decimal than I got? Okay. Oh, yep. Thank you. I must have pushed a button wrong somewhere. That happens when I text too. I got large thumbs and it just happened. So 0.0316. Is that what you said? We agree now? Awesome. Thanks for keeping me honest. I appreciate that. All right. So now, if you're good with everything else, let's go down to example 7. I'm going to give you a minute or two to go through those 3 problems. You're using the spinner this time to determine the probabilities. Well, we saw this. You just did it. So 25% is what as a decimal? There you go. You got it. That's the red on getting red on one spin. Yeah, so it's red on both spins. So since that's an and problem, it means probably red and red. So you're going to do probably red on the first one times the probably red on the second one. What is out of 100? Okay, so let's recall, because we saw this spinner and it's been like 3 weeks because of spring break. So when I'm doing the spinner, okay, if you want to use fractions, what we can do is we can cut this into equally sized parts. Okay, so if I'm doing the probability of red on both spins and I'm using fractions, well then what's the probability that it lands on red? How many red spaces are there of equal size? There's 1 out of 4, and that's the 0.25 that you gave me earlier. So you can use decimals on this. So I'm going to do this your way. So this is how I would have done it, but then this is what you said. It's 0.25, great. So then now I spin it again. What's the probability it lands on red the second time? Yeah, 1 out of 4 again. And so that's going to be 1 out of 16, or we can make that into a decimal. But if you use decimals, it's 0.25 times 0.25. Decimals represent my probabilities or fractions. We can use either. And when you do that, 0.25 times 0.25 is 0.0625. Okay? Either way. So the next one, the probability green and yellow, what's the probability it lands on green? Yeah, you can either use 1/2 or you use 0.5. I mean, 50% of the area is green. Okay, that's a great way to look at it. Told you back when we were talking about probability that there's a relationship between the amount of area and the probability. In fact, I think we did that goofy problem that had the triangles and the different size rectangles, and we saw that same thing there. And then yellow is the same thing as red. It's 1/4. So 1/2 times 1/4 is 1/8. Over here, if you'd use the decimals, 0.25 or 25% of the area is yellow. So 0.5 times 0.25 is going to give me 0.125. Either way. Lastly, I asked you, okay, let's not get stuck in a rut of doing everything twice. Okay, because this and thing applies to any number of multiple trials. So if I spin it 3 times, what's the probability they're all red? Okay, well, what's the probability I get red on the first try? 0.25 or 1/4. What's the probability I get red on the second try? Yes, indeed. And one more time, just to make me happy, what's the probability we get red the third time? Yes, there you go. And so you just do it for each spin. So 0.25 times itself 3 times is going to be 0.0156. Are we still checking my multiplication? Am I doing okay with my calculator? All right, last thing then, last problem, just to make sure that we are 100% certain on this. So I've got this situation where on a shelf, there's 7 DVDs, there's 4 dramas, there's 2 science fiction, there's 1 comedy. I'm going to select 2 movies at random. You're going to determine the probabilities. There's 2 probabilities. What's the probability of getting a drama and then a comedy? What's the probability of 2 comedies? But you're going to do each problem twice. You're going to do it with replacement and without replacement, just to practice all of this terminology that we're dealing with. All right, so just going through this, I'm going to first do these with replacement. I'm going to do them with replacement in orange ink right here. So I'm going to draw a little wall. We're going to do the with replacement on the left and the without replacement on the right. So let me write that just so that it's super clear. So if I do this with replacement, first, what's the probability that I pick a drama off the shelf if I've got my eyes closed? Yep, there's 4 out of 7 are dramas. I am replacing that movie because maybe I didn't want to watch a drama. And so now what's the probability that I pick a comedy the next time? Yeah, 1 out of 7. So that's going to be, if you made a fraction, it's 4 out of 49. If you made a decimal, that's going to be 0.0816. 2 comedies. The probability I pick a comedy the first time you just told me is 1 out of 7. I replace that, so the probability I pick a comedy the second time is, yep, does not change. These are independent events because the probability of the first thing happening does not change the probability that it happens the second time, and so I get 0.0204. So far, so good? All right, well, now we're just going to redo these same 2 problems. We're going to do it without replacing the movie this time. So drama and then a comedy. The probability of a drama does not change. It's 4 out of 7. What's the probability that I get a comedy if I do not replace that movie? Yeah, you have 1. You still just have 1 comedy, but now we only have 6 movies left on the shelf. So that's 4 divided by 42, and that is going to be 0.0952. Then the probability of 2 comedies if I don't replace. Well, the probability the first one's a comedy doesn't change. It's 1 out of 7 times. I am not putting that comedy back on the shelf. So what's the probability that I get a comedy with the second one? Yeah, there's no more comedies. 0 out of 6. So 0 times anything is 0. That can't happen, which kind of makes sense. There's only 1 comedy movie on the shelf. If I'm not replacing, I can't draw 2 of them off the shelf. So there we go.